can really be written in, this is it actually. This is your entire engineering, no matter what engineering. So tell me what engineering problem you have and I'll tell you that how you can write it in this manner. Okay? So your entire physics is sitting here. So this is not a simple thing. It is really a powerful thing. So I just want to kind of give you a feel. I don't need to tell you that from QR codes to networks to your machine learning and data science and your aerodynamics and whatever you are doing, one way or other way, all of the problems are broken in the terms or can be broken in the terms of linear algebra. Okay, are specifically in the terms of this AX equal to BX. So I'll take some particular examples and try to give you a feel for this AX equal to BX and show you that these ideas are pretty useful not only in the basic things that you see, but the non-trivial things actually, the things that can actually solve some complicated kind of problem solving. So I'll give you some examples of that. All right. So what are some of the key ideas from linear algebra? So when you learn linear algebra, you start with vectors and do the algebra of vectors. So algebra is nothing. It's just that you take two objects and you do something with it and try to create a new object out of it, but of the same species. Okay? This is an important thing that you take two arrows. Okay, so you take two arrows. Okay, and you do something with them, and then you create a third arrow out of it. Okay, and the different people have different what you call conceptions of linear algebra. I mean, if you ask from a computer scientist what is a vector, the computer scientist will tell you that okay, for me, this is what a vector is. Like a list of numbers. That's what. I mean, if you ask from say a physicist, they'll tell you that this arrow is is the vector. Okay? But mathematicians are more gravier, so they just can turn almost anything into a vector. So a function would be a vector, a matrix would be a vector, a number would be a vector, and so on and so forth. Okay? So these are powerful ideas. But I'm gonna stick to this. Okay? Let's say that I want to convince computer scientists, okay, that this list of numbers, when you combine them with matrices, becomes extremely powerful. Okay, and then the next thing that you learn is basically what you call linear combinations and spans and bases. Okay, you have heard these terms. You all have heard these terms. So I don't want to bore you with the maths actually, but I want to give you this one analogy, and that analogy is really going to demystify almost everything, which is that so you can imagine in your head that each vector is like a color actually. So it's a color. Okay. So each vector is a color, and we know that we are a species, so which can identify three colors and its combination. Okay. So when you see a color printer act, आप color printer एक देखते हैं उसका toner अगर आप open करें तो कौन सी inks मिलती हैं आपको? You just have three inks, so R, G, and B. But it turns out that using these three colors, okay, you can create almost any color you like. You can print almost any color you like. So each color is like a vector. Okay, so it's like a vector. And what does this vector is telling you? This is telling you that take this much scoops of say red color and take this much scoops of say blue color and take this much scoops of green color, and you're gonna get whatever color you like actually. So each color in this, what you are actually seeing is basically a combination of three colors. So whenever you have so think about now. So as I can say add vectors, so now I can say that I can add colors, and the addition of the two colors is going to produce a third color. Okay? And the vector algebra is nothing, it's just mixing of colors and producing the new colors out of them. Okay? And like what you are looking at is, if you have encountered the notion of something called vector space, like this is vector space of colors. Just a part of vector space of colors, that in which you have different colors, but I know that all these colors can be obtained from R, G and B. So R, G, B are like the bases. You also would have heard actually that you have something called basis vector. Yeah, you must have seen that you say that you take 2I and 3J and this is what my vector is, 4K. Yes. So what does this is telling you? It is telling you that so I is like a color. Let's say this I is like red and J is like blue and K is like green. Okay? And you are saying that take the 2 scoops of color R, 3 scoops of B and 4 scoops of G, and this is what is really a vector. And a vector is a color actually. Okay? And now I'm saying you that just go back and see all of your complicated equations of linear algebra, and you will see that all they make sense because there you are doing nothing, you are just trying to produce new colors out of 3 colors. And this, this object. So this is like a linear combination. So when you take a linear combination, what do you actually do? You say that give me some basic vectors, okay, like I and J and K, and I can produce any vector I like that. Okay? So, in other words, this vector is a linear combination of 2 I's and 3 J's and 4 K's. So, similarly, this is a linear combination. So, when you are saying that you are doing linear combination, what actually you are doing is that you are taking some scoops of red color and some scoops of green color and some scoops of blue colors and putting them together, and you got you create a new color out of it. Okay? So, the vector algebra now try to interpret all of your things that you have learned previously in your linear algebra course in the terms of colors, and you will see that everything makes sense. Okay? These ideas are really interesting kind of ideas. And really, another thing that you emphasize so much on in your courses is this, solving this AX equal to B diagram. Okay? And I want to give you a feel for it, and then actually show you some stuff actually that what I'm trying to say really works actually. Okay? So now, if I'm taking A and I'm multiplying with X, is it visible? Yes. And I'm taking it B. So what I want you is to interpret A as an action. So just read this thing as an action. So this is, A is an action, and X is an object. It's an object. And when you do this action onto this object, it produces a new object. That's a new object. Is it making sense? So interpret A as an action. Now what action do you know, for example? Okay? Say for scaling of it. Now scaling is an action. Okay? Or you shrink it, or stretch it, or rotate it. Okay? So like a computer graphic for computer graphic person, the action is like all these things. You translate it, you rotate it. Okay? Say for example, if you are in physics, okay, for you, for the physicist, this A is an action, but this action could mean something. Okay? What it could mean, for example? It could mean, for example, let's say, it can mean, say that, okay, you have this quantity X, okay, and give me what? Let's think from the point of view of, say, finance guy. Okay? So the finance guy is going to do what? So for a finance guy, this X is like, say, so here's the thing. So X is like its portfolio. So it's like, X is like an investment strategy. Okay? It's an investment strategy. In other words, आपके पास 4 stocks हैं where you can put money. आपके पास $1000 हैं और आपके पास 4 stocks हैं. And you want to make, what do you call, money, and you want to invest these $1,000 into your stock. Okay? So in order to make an investment, what do you need to do? So you want to minimize the risk and maximize the profit. That's what you want actually. So when you're, what do you call, try to make an investment, this is what is your sole purpose. Okay? So you can interpret, for example, this. So X is your strategy. Okay? And action of A is like you want to minimize the risk and maximize the, profits. Okay? So in other words, this A can have any interpretation you like. So always see AX equal to B as an action that turns your favorite quantity into some other quantity. Okay? So that's what you have to always keep in mind. For example, so one example that I gave you that, yes, you can also think from like this could also be in physics. You can also interpret it in the terms of physics, or you can also interpret it in the terms of computer graphics. That if you take this matrix A to B, say for example, this matrix 2, 0, and 0, 1, okay, and you multiply it with some vector, what it is going to do, it is going to horizontally stretch that picture. I'm going to show you that this stretching is really happening. Okay? And if you take, for example, this matrix, it is going to take your picture, whatever picture you have, and it is going to rotate it 90 degrees. Okay? So that's a 90-degree rotation. Okay? And this is shear. Okay? So it's like a shearing. So let me show you actually that how it could be done. Okay? So I prepared a few things for you. Forget about what you are seeing. Let's say that of all this. And let's say that you start with a point out. Let's say that from the single input the single input here's the thing. Let me seems like Pentium 0 now. That's good though. Let me add this Pentium this last time. Anyway, so let's take one of the matrices that we saw. So one matrix that we saw previously was what? Let's say that I'm taking 2, 1, and 0, and that the other was 1, and the next entry was 0. Okay. So what is happening at the moment is that you have this matrix, okay, and it is acting onto this vector, which is this purple point at, okay, and it is producing this one. Now it doesn't appear actually that what is going on, but if I move a little bit, okay, you see that something is going on. But that's something I can't interpret it at the moment. So let's say that now, instead of taking one point, I take a grid of points. Okay. Let's say these are my points. This is my grid. Okay. So each point of this grid has a coordinate. सबको पता है ना coordinate? So uske coordinates. So what I'm going to do is that I'm going to take, for example, the coordinates of say this point, or maybe this point, which is 1, 0, and I can multiply it with 2, 0, and then I can get a, what do you call, another, point actually in this case. Okay. Now, in order to really see, अब ये होगा कि like this is like you are inputting one vector. How about if I multiply this entire grid at once with the entire matrix? Okay. So what is going to happen? Now we can see. Okay. Now we can see. I need to show the outputs. So these red points are inverse. So now we can see that what is 1. So what was our first claim there? This last entry should be. ये 0 होनी चाहिए और ये I make a mistake, please tell me. And now let's see what happens. Say like we get rid of the points of the inputs. So inputs are red points and the outputs are these points. So what is happening? What is happening? So in other words, as I'm increasing the value of S, what is happening is that this matrix is repeatedly being multiplied with each point after. So let's just interpret this, that what is going on. So you take a point, okay, it has some coordinates x, y, and you multiply it with matrix, so it is going to produce something else. Okay? I don't know, say AB. This is going to be like too much. So it is going to produce new point. How about if I repeatedly multiply this? So what is going to happen? So always the new points will produce.
Yes.
So when I'm changing the S actually, this is what I have prepared. So it's like I'm repeatedly multiplying the matrix with these inputs, red inputs, point actually. Okay, and I can see that when I'm repeatedly multiplying, okay, my red inputs with the given matrix, say A, so it is producing this impact of, structure. Okay, and I can quickly change, for example, more the other matrix. 0, negative 1, right? Rotation matrix. The negative 1, 0. 0, 1. Now let's see what happens. Already predict actually that now my grid is being mutated. Now my grid is being mutated. So in other words, this action of the matrix A onto these red points is producing, so these red points is producing the effect of rotation. Effect of what? Now you could see, okay, so what? So what? Now, what's interesting is, now I'm going to say, think about, so let me now replace this grid by something else. Let's say I make a smiley face out of, these dots. Okay, these dots. So what will happen if I do the same? I think there is. What will happen? This is doing this shear thing. It should be a shear matrix. Yes, it's shear. So let's say that if I do 0. 0 and 0, 1, right? Yeah. And let's see what happens. So, reducing stretch. Matrix fatigue. 0 negative. 0 negative. I think that's something wrong is going on. 0 negative 1. And 1 and 1, 0. ये क्या आएगा 1 आएगा 0 आएगा ये ठीक है सही बताओ I can do this so here is and I can do my so क्या होना चाहिए ये let's start with again 1 या negative 1 0 अच्छा उसके बाद आ गया negative 1 ये होना चाहिए 1 so that's a, so I'm just picking the rotation matrix 90-degree rotation okay so when I'll do this so let's see what happens so it is producing rotation but okay something is wrong with the inputs otherwise it would have produced only rotation so it is producing the you see that it is producing the rotational effect at least there is rotation okay there is a stretch as well and a rotation the matrix is correct. I think there is nothing wrong with the matrix. Maybe something went wrong in the inputs. But this is what that is. So why then this is interesting. Now think about it. When you are watching a video, what is your screen? So it's a matrix of pixels. And what is happening is that these pixels are changing colors actually. Okay. Now, if you think what is going on at the back end, for example, you take a picture and you rotate it 90 degrees, your image. So what is happening is that at the back end, your computer is doing what is taking this matrix, then it's multiplying it with the rotation matrix, and it produces the rotated image. Are you getting the point? Even all of the videos and imagery that you see, it could be interpreted. So at the back end, there is nothing else happening. It's just you have a picture and a different kind of, matrices are being multiplied. Okay. So I mean, you think actually that, for example, you have an image. So you have this image. Okay. Maybe you have this image A. And I multiply it with, say, a matrix, say a rotation matrix. So it is going to do what? It's going to rotate this image. How about if I, multiply it with a stretch matrix? So it is going to rotate and then stretch it. This is what is happening actually at the back end. So nothing fancy is going on. It's like you are taking some input, which could be a matrix and a vector, and this is something that is an action is happening on what you call this. Okay. Okay. One last thing, and then we'll move to the examples. Okay. The examples. This is boring stuff, I know, but this is important to at least see that what's going on. Okay. So another example that you see, and you never probably understood, is that something that everyone hates. When I studied first linear algebra, I also did this. It's called the eigenvalues. Bloody hell. Okay. Eigenvalue problem. So what do you do when you do the eigenvalue problem? So you say that for a matrix, the eigenvalues and eigenvectors are something that satisfies this. Okay. But what would be the physical meaning of it if I have to understand? The physical meaning of it is going to be, to really interpret it, is that you take this vector, okay, which represents something, okay, and you multiply it with once, okay, it is going to produce something else. You multiply it with again, it is going to produce something else, and you multiply it with something, and you repeatedly multiply. And you ask that if I keep on multiplying this, new thing with this matrix A, what is going to happen in the end actually? So what is going to happen is that a time will come when this will stop changing. Okay? And it will point in some direction. Okay? And that direction is going to be the direction of eigenvector. Okay? An eigenvector. So what does it mean? It tells you what is, so eigenvalue problem is telling you that what is going to happen in the long run if you keep on doing the same operation onto it. And I'll tell you later, I'll show you the examples. This is precisely how the Google search works. So if you are making a Google search, this is what is happening. Your Google, okay, is basically solving an eigenvalue problem at the back. Okay. So Google algorithm is doing it. I'm gonna show you. But I can also show you here actually. Think about it. I can also show you here. So I need to change this method. Maybe I change it to 0. Just cutting. I can show you this. So here are the eigenvalues of this. The eigenvalue of this is 0. I can show you the lines where it goes. This is the line that has a slope. Okay. Now my claim is that if I pick a point and I multiply it with matrix A, it is going to come down. You again multiply it with matrix A, it is going to come down. But you will see that this line is a strange kind of line which is like attracting all these points up. Which is attracting these points. Okay? So this eigenvalue, so let's try to see that. Can you see that what is going on? So what I am doing is I am repeatedly multiplying. So every movement that this dot is making, okay, is basically taking that dot and multiplying it with the matrix. So what is happening? What is happening is that these points are kind of being sucked towards. Okay. Can you see that? Okay. Since it has to do a lot of computations and this is not a good computer, so this is what happens. Are you getting the point? So see, everything is, all of those dots, okay, they are being attracted towards this line actually, which is basically the, which you get through the eigenvalue. Okay, this is what is happening. Isn't that an interesting thing? So in other words, this eigenvalues and eigenvectors are basically the directions in which all of the vectors are going to, go if you keep on doing the same action again and again. Okay. All right. Now let's get back to that. So I hope that so you could treat this as the crash course on. अभी तक जब हमने पढ़ा है, it's like a crash course on linear algebra. ठीक है? आपको vectors की manipulation को imagine करना, imagine them as colors. Everything is color. आपको eigenvalue problem को imagine करना, imagine that you have these points